So now that we have Faraday's law, let's talk about the different things we might do with that time derivative. So one of the ways that we can have a changing flux is to actually change the area. Now note for all of these that I'm assuming that we have a uniform magnetic field. So if there's an integral in the flux, this whole thing becomes a little more complicated. So we're not going to talk about at least that case, but that could happen in general. So assuming that we have a uniform magnetic field, the angle that our magnetic field is making with respect to our area vector can be changing. So in that case, you would be taking the time derivative of cosine of theta. This comes up a little bit. There's going to be an example of a generator that uses this, but it's the least common. So know that that can happen, but it's not going to be the one you see the most. So then another thing you can do, instead of just thinking about taking the flux and time derivating the angle, is to actually expand this out and think about the chain rule. In that case, you get two terms. Now, in here, we really rarely have to use both of them. You usually have either the area changing or the magnetic field changing. So your area changing would be this term. Your magnetic field dotted with that change. And again, you can assume the angle staying the same in most of these cases. A different scenario would be that the magnetic field is changing and the area stays the same. Now, the area changing could be like that emotional EMF example we did where one side is sliding. You could have something that is expanding or shrinking, like someone grabbing a wire and crumpling it up, or taking kind of a coil and stretching it in some way. Now, changing the magnetic field, there's actually a couple different ways to do that. One is to change the current. If you have a loop or a solenoid, i.e. an electromagnet, generating your magnetic field, then increasing or decreasing the current will therefore change the magnetic field. You'll see that a lot, and we're about to do an example with that. Another option is changing the distance. This is going to be the case, for instance, whenever you're using an external permanent magnet. Now, this you're not going to see very often in calculations, but you would have to think about how the magnetic field is actually changing with the distance that whatever your loop is that you're inducing a current is from your source. And one of the things you'd want to think about here is that we have talked about how the distance affects magnetic field in a dipole if you're on the axis or if you're perpendicular to the axes. So typically the only time we're going to do a change in distance is when we have a dipole field. So think about that. Obviously, if you have a uniform field, then you don't get a change in magnetic field based on distance. You also might just be told something more explicit. Like you might just be told that your magnetic field goes from this to that over this time. So do think about all of these different terms. And again, recognize that all of them give you a changing flux, which means in all cases you are inducing an EMF or current. I say EMF/current since EMF is really kind of what's foundational here, but then frequently you're going to be asked to actually figure out current. So let's look at an example. In this case, we have a solenoid and a loop. So the loop is like a ring or something inside the solenoid. So you know that a solenoid generates a uniform magnetic field inside of it. So the first question you should ask is, hey, is my flux changing? Because if your flux isn't changing at all, then there's nothing to calculate, really. But in this case, we actually have a current that is changing with time, right? And in this case, this is the solenoid current. Because your solenoid current is changing with time, that means the magnetic field that the solenoid produces changes with time. If the magnetic field that the solenoid produces is changing with time, then your flux is changing with time. So when we think about the flux, in this case, again, the magnetic flux, we want the area of, I'm going to call this the loop, right? That's this thing. So your area is just this circle. It's not the area of your solenoid. And then it's the magnetic field from your solenoid. So that's what this is going to be. In this case, I can drop cosine of theta because notice that your area vector is that way. So this is a case where your area vector and your magnetic field vector are parallel. Theta is 0, cosine of 0 is 1. So then when I say what is d phi dt, this is a case where area stays the same and I'm going to have dB dt. Now then you would say, well, how does my magnetic field relate to current? And you would get di dt from this plot. So notice in this section of time, di dt equals 0, and in this case, your induced current equals 0. So in this early time over here, you do have an induced current, but after 1 second, you would not. So again, it's important to remember that it's the change in flux that induces a current, not the just absolute value of flux. So I'm not going to do this calculation in any more detail. It is in the book. But again, just to clarify the notation, make sure that you're using the area of whatever loop you're interested in.